तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been discussing the IV characteristics of Schottky barrier diode, and when we were doing that, we arrived at the ideal characteristics, and we have discussed. I just summarize what we said last lecture. We have seen, or the experiments have shown, that the IV characteristics deviate from the ideal characteristics. For example, reverse current does not saturate, it will keep on increasing. Forward, I is I naught e to the power of, instead of being V by V t, it is V by n V t. That is, less it increases less rapidly with voltage. So, we just also said we considered only this current, that is the thermionic emission current, and these are the B, C, D are the various terms which we have neglected, and out of that we have seen B and C we have seen yesterday or in the previous lecture, that is hole injection into the neutral region and recombination. That we said it is not going to matter much, we analyzed it, making use of the law of the junction, p-n junction. Similarly, generation recombination current, it is much smaller compared to this particular current, thermionic emission. So, we also do not have to worry, it is at least 1 or 2 orders of magnitude smaller in gallium arsenide. So, let us see, the other term that we have put it here is the quantum mechanical tunneling. So, these two terms are negligible. So, other terms which are there are image force lowering of the barrier and quantum mechanical tunneling and insulating interfacial layer. These are the three things which we are going to discuss today. Now, image force lowering we have just discussed fairly in detail what it is going to be. It is due to the negative charge as it comes close to the metal, its mirror image is on the other side. So, the charges induced on this plane can be, the effect of that on this charge can be obtained by considering the image of this charge there. It is simplification, it works out very well. Otherwise, you have to take, you do not know how the distribution is, but entire effect can be accommodated by putting the mirror image here. So, that means actually this charge experiences a force which is actually equal to q squared by 16 4 pi epsilon x squared, where x is the distance, okay, and as you go nearer, okay, the charge, the energy, okay, and the force, both of them keep on increasing negatively. So, that is why energy is integral of that. I am just going through this quickly because we have discussed it yesterday. Okay. That is the energy integral of the force, q squared by 4 pi epsilon x instead of x squared, and potential we are talking of electronic potential. Okay. That is actually minus. Okay. So, what we are just trying to point out is, if I move from here to here, the electronic potential is that quantity, okay, that is 16 pi epsilon r epsilon 0 into x. And as far as this charge, the field is concerned, plus there and minus there for this, negative charge and plus charge. So, field is in that direction. Okay. So, it moves, the energy of the electron will lower negative as you go towards the metal surface. So, that is why we are actually talking of electronic energy and electronic potential. So, energy level and electron potential will follow the same path. So, if energy level is dropping down like that, electron potential also will drop down like that. Okay. These are lower energies for electron. In fact, if you recall, zero energy is there, all the other energies are negative, negative, negative. Okay. So, that is what we have plotted there. Okay. So, if you look into that, that is the one which is going down in this fashion. Now, in the absence of the image force potential, this is the image force potential psi. We usually plot the energy band diagram like this. In fact, that is the variation of the electronic potential or variation of electron energy. Okay. How do you obtain that? You just have the depletion layer there. We call it here as E external, because this one is due to its image itself, but this field is due to this depletion layer. If there were no depletion layer, then this would have been only the potential. Because of depletion layer present, there is additional external force acting on the electron, and that is actually given by this. That is electric field E external, which is given by E peak into 1 minus x minus by W d. That is what we have put here. Okay. That is the electric field. We called it as E external. This is the regular depletion field we are talking of, and psi potential is actually integral of that. Okay. In fact, in my last lecture I just left out this T, but the 2 is there. Okay. Now, what we do is, what we are trying to find out is, there are two potentials now. Potential due to this image psi if, potential due to this depletion layer, which we call it as the E external. Okay. The total potential is sum of these two. Now, what I have done here is, to simplify matters, I have just neglected the second term, this term. You can neglect the second term so long as x by W d is very small compared to 1. Okay. We are actually interested in the potential variation just near the boundary. We are interested in the potential variation just near the boundary. Okay. Because we are interested in seeing what is the effect of this image force potential and the external potential. Okay. Add this and this. Sum of the two is given by, if I approximate the external potential by this way, E peak into x, then you have got these two terms. You add up those two, that is the, you can call it as delta phi, that is potential with respect to that point, or total psi itself. Better to call it as a total potential. Okay. So, the potential is sum of the two. Now, whatever approximation that we have made here will be true if this x m is small compared to the total depletion layer width. We will see that that is really true. The peak occurs very close to surface, okay, in the order of 10 to 15 angstroms compared to 0.3, 0.4 micron of depletion layer. Okay. So, that is why this approximation is quite good, because we are talking just in this diagram it is not so, it does not look so, but it is actually very small. So, what we want to find out is, what is the total variation potential? More than that, what we are interested in is, what is the peak value here? Because after all, maybe I can explain here, after all this potential is varying like that. That is the external potential due to depletion layer. This potential is like this. Total potential is this plus that is this one. In this portion, okay, this is, suppose you consider this as 0, this is negative. So, this follows that. Then when you go down here, that is 0 and this is the potential. So, this is 0 here, this is the potential, total potential there. So, that is why the variation is like that. So, to find out this value here, what we do is add up the two, okay, and we know that it goes to a maximum, differentiate this term with respect to x, and when you differentiate with respect to that, what do you get? You get x is equal to, x is x maximum, that is root of that. It is a simple differentiation. So, this becomes square 1 by x squared, this x goes off. So, you get that. So, the location of this particular peak electric field is actually given by this quantity. Now, once you do that, what you want to find out is how much is the this difference from the top to that point. which we call it as delta phi V n. Okay, now, let me go to the board and show that to you. So, the actual potential now, instead of being like this, it is like this. It is like that. Okay. So, let me draw it slightly better, because that is very close by. So, this entire potential now will be, instead of being like this, it will be now like this. So, this quantity, now actually this quantity is delta phi B n. Why do you call it delta phi B n? This is the potential barrier which would have been present, but now because the barrier does not go all the way up to that point, it goes only up to this point. As a result, there is a reduction in the phi B n. This is called the image force lowering effect of the barrier height by that amount. How much is that amount? That is same as this potential. See, please remember, the potential we are drawing, taking this as 0, with respect to that, how much is the thing? The psi that we put there is psi with respect to that, because that was 0 there and that was psi image force. This is, if I take it as 0, that is the potential. So, if I find what is the psi value here, that straight away gives me delta phi B n. And how do you find psi value there? Add up the two, substitute that. Let me just write that down here. See, we have got psi is equal to minus E peak into x, okay, minus q divided by 16 pi r epsilon 0 into x. Now, we also seen that, so psi maximum will be what? When both of them are equal. See, one is coming like this, other one is coming like that. The peak will correspond to this point where both are equal. So, that is actually twice E peak into x, x m. Substitute value of this quantity, we have found out the point at which it is maximum. In fact, you can verify that, just going through that, that is the value. Okay, so, substitute for this quantity from the expression for x m. Let me not write down that, because you already have got that. All that I am doing is substituting for this x m, which we have determined as, by differentiating, we have determined that as this quantity. Okay. So, substitute in that equation psi m is equal to twice E peak into x m. So, you do that. All that you have to do is multiply this quantity by twice E p. So, 2 goes inside the square root, that becomes 4, 4 divided by 16, that is 4 here, and you are multiplying with this by E peak. Okay. So, square root of E peak is there in the below, so that becomes proportional to E peak. Okay. All that we are doing is that. I hope it is all right. See, what we are doing is x m, that is actually minus twice E peak into square root of q divided by 16 pi epsilon r epsilon 0 into E peak. So, this becomes square root of that, this goes inside, this becomes 4. That is how we get that particular term. The key thing to remember here is that this potential, I have called it as delta psi maximum, that is this quantity. What we have computed is psi, psi is the delta psi maximum. Maybe unnecessarily I have introduced one more term there, just differentiate this related to this barrier. So, barrier maximum reduction is that. Okay. If that is delta phi b, the actual barrier is this much. So, if the actual barrier is this much, the electrons can go from one end to the other end very easily. So, the current can get affected, that is what we are trying to point out. Okay. Now, let us just take a look at the effect of this particular barrier lowering. So, delta phi b n is the value of psi at x m, that is what you have determined, that is proportional to square root of electric field, peak electric field. Okay. Now, before we go into that, we have derived this by taking the E external is E peak into x. Okay. Now, let us see whether it is valid at x equal to x m. For that, we must find out how much is x m is. Okay. Let me just give you some numbers there. How much is the value? Say, let us just take this. X m is equal to square root of q divided by 16 pi E peak. Okay. So, all that we have to do is what will be the value of E peak. E peak in the depletion layer. See, E peak corresponds to this peak field, that will be roughly 10 to the power of 5 volts per centimeter, 100 kV per centimeter, 10 to the power of 5 volts per centimeter or 10 volts per micron. If you go to 20 volts per micron, you may have breakdown. That is why I am giving that number, less than that, but close to that. 10 volts per micron, that is okay, 10 to the power of 5 volts per centimeter. You substitute onto this with the epsilon r taken as 12.8, 8.84, etc. This is approximately about, if you take that is about 20 angstroms. Okay. You can just plug in and see numbers. This is about 20 angstroms, 2 nanometers. What we are telling that is, because of that is, this peak occurs very close to surface, and this x m is very small compared to W d. So, our assumption that in the region up to this point, this potential is linear is very much valid. So, we took, while deriving at this expression for delta phi b n, we took E external is equal to E peak into x. Now, we are talking of that only up to x equal to x m, and x m is just very small compared to depletion layer width. So, that is valid. So, we are justified in doing that. Okay. You are not assumed the electric field as constant really, but you have actually seen that potential is varying linearly and that up to that point. Okay. Now, other thing that you would like to see is how much will be this barrier lowering. Should we worry about that? Because after all, we have thrown out other numbers with the hole injection, etc., because they were all not comparable. They were not comparable to J naught, etc. So, let us take a look at that now. Delta phi b n, order of magnitude, how much? That is what we want to see. So, delta phi b n is actually equal to root of q E peak divided by correct? It is right here. Delta phi b n is that number. Now, what you do is substitute for this E peak. Okay. It will be about 10 to the power of 5 volts per centimeter E peak. We have taken that, and the depletion layer width is something like 0.3 micron for about 10 to the power of 16 doping. So, for this situation, this turns out to be substituting all these values, something like 10 to the power of 5 volts per centimeter. If I take substitute for epsilon r 12.8 for gallium arsenide, 12 for silicon, epsilon 0. for gallium arsenide, epsilon 0 is 8.854 into 10 to the power minus 14 farads per centimeter. Substitute all that, you get this about, in this example, about 35 milli electron volts. Okay, that is about 35 milli electron volts. So, that is not negligible, because after all the J naught value that you talk of is proportional to e to the power minus phi b n by v t. So, if that were phi b n naught and if it is 700 millivolts, this is 35 millivolts. You will say 35 millivolts is small compared to 700 millivolts, but if you take e to the power of that quantity, the currents are proportional to e to the power of minus phi b n by v t. If it is 25 millivolts reduction, it is e to the power of 1. E to the power of 1 is 2.7. So, the current is different by magnitude of 2.7 for 25 millivolts. So, even if you are talking of just 10 millivolts change, that J naught will keep on changing, okay, because it is exponentially dependent on phi b n. So, any change in phi b n is reflected on J naught. So, now whatever changes you see in the reverse bias and forward bias are manifestations of delta phi b n, that is effectively J naught changing. So, what is done is, okay, let us see how it affects in the case of forward bias. In the forward bias case, what happens to delta phi b n? Delta phi b n depends upon E peak. If delta phi b n increases, what happens to phi b n? Go back to this diagram and see, if this increases, this falls, phi b n. Okay. In the forward bias case, what happens to the E peak? As I keep on increasing the forward bias voltage, what happens to the external field? It reduces. When the forward bias, the depletion layer collapses. So, peak electric field falls. So, when the forward bias, peak electric field falls. And if it falls, okay, delta phi b n reduces. If E peak falls, delta phi b n reduces. If that happens, phi b n increases. So, starting from 0 bias, see, we take 0 bias as some phi b n. Let us take the J naught corresponding to that phi b n. Okay. From there, it either will go up or go down. See, what I am telling you is, even at 0 bias, the value that you have is not the same thing, it is different. But from that point onwards, it will go up or down depending upon whether you are forward biasing or reverse biasing. So, in forward bias, electric field falls. So, phi b n actually, electric field falls, therefore, this falls. So, that goes up, phi b n increases. So, if phi b n increases, what happens to J naught? Reduces. Okay. Now, usually we write the expression for the forward characteristics as J is equal to J naught e to the power V by V t minus 1. Now, what is done here is to take into account the entire characteristics. You keep J naught constant, and whatever changes that take place with J naught, you absorb into that term n. So, when you forward bias, the value of J naught actually what happens? It decreases, because the barrier rate increases. So, that decrease in J naught would, if you put n is equal to 1, you have to keep on changing J naught, and that decrease in J naught will reflect in the J not increasing as fast as e to the power V by V t. So, if I say J naught is changing, it is reducing, the implication is current does not increase as much as it would be. See, for example, let me remove that and put it. If I write J is equal to J naught e to the power of V by V t minus 1, I get a characteristic which is varying like this, J versus V. if J naught were constant. But if J naught is going on falling as I increase the forward bias, because peak electric field is falling, if J naught is falling slightly, for a given voltage, this current will be lower. So, you will get actually the current which is slightly lower all through cases. Strictly it will slightly deviate from this particular curve or slightly from ideal exponential value. So, this reduction is taken into account. You assume that this is constant, absorb that into that factor n. This is sort of urging. Okay, you are just cooking up a number n there, which will be greater than 1. So, current will increase slower than what it would be from the ideal. The entire effect is due to J naught falling, but you keep J naught constant corresponding to 0 bias, and then say that there is a n which is larger than 1, that is a non-ideality. So, this term is quite it is definitely more than 1, because the phi b n, the delta phi b n from the 0 bias case is always 5 millivolts, 10 millivolts of that order as you go on changing. It may vary 1 millivolt, 2 millivolt, 3 millivolt, 4 millivolt like that, but it affects totally. What about reverse bias? It will show up much more. Reverse bias, what happens to peak electric field? Increases. If this widens, it increases, and if it increases, you can see from here delta phi b n actually increases. If delta phi b n increases, if that increases, this falls phi b n. So, as we go on keeping reverse bias, the delta phi b n goes on increasing, phi b n goes on falling. So, this keeps on falling. It is e to the power minus. So, if this keeps on falling, J r keeps on increasing. This will be much more dominant in this case, because if you have a 25 millivolts change in the phi b n, which is quite possible because peak fields are more increasing quite a bit, where current can be double reverse current. That is why you get the reverse saturation current not saturating, keeping on increasing. So, both the IV characteristics in the forward direction and also in the reverse direction, that instead of being like this curve now will keep on increasing, not due to generation recombination, but due to image force lowering effect of the barrier. Okay. So, barrier height keeps on falling, that is why this is happening. So, now you will be in trouble if you have devices made in certain portion of the device. If there are large fields, reverse current will dominate quite a bit. It will leak through those portions because of this image force lowering. Okay, now let us see what other thing is there on here. So, I hope this explains as a dominant phenomena for deviation from ideality. Okay. This is just a formula which I have just put here. All that we have done is delta phi b n is q by this quantity, and this whole thing within the square root sign is peak electric field. Okay. That is peak electric field. Peak electric field is, let me just put that down here. This is for computing the numbers, that is all. So, peak electric field is q and d w d divided by epsilon r epsilon 0, and V b I minus V. In the forward bias case, this is negative. If V is reverse biased, this is adding. That is actually equal to what we do is substitute for that from here. So, therefore, this is equal to what? So, W d is a standard formula. That is W d, and when I put it here, E p becomes square root of, I substitute from here to there. Okay. So, that becomes equal to root of this, and that cancels there, q and d and square root of that, root of q and d, okay, into V b I minus V I V V b I minus V, okay, divided by this is the denominator, this is the numerator, divided by epsilon r epsilon 0, okay, into there is a 2 term, that term, that is 2. So, all that I have done is whatever I have written on the board there, that is the square root term. Okay. Delta phi b n is square root of q by this quantity into E peak, that E peak is this quantity. So, the formula looks big, but it is actually a simple formula where we have substituted for peak electric field from the well known law of junction. Then when you do that together, it is square root of to the power of 4 and all that comes, because this is square root, this is square root of to the power of 4. So, delta phi b n is actually a function of v to the power of 1/4, v to the power of 1/4, that is what we are trying to tell there. It does not vary directly as v, not as square root of v, but is 1/4 total potential. If it is forward biased, the V b I minus V, and if V is minus V r, V b I plus V r. So, that keeps on increasing. So, now from here it is very evident that delta phi b n will keep on increasing if V is minus V r. If V is forward bias, this quantity goes on decreasing, delta phi b n goes on decreasing, and decrease of course will be small in the forward bias case. The impact of that will be not too much. So, you will get instead of ideality factor 1, you may get 1.05, 1.06, that is all what you get. So, we are making so much fuss about that, but you have to really make fuss about it in the reverse bias, because that current will shoot up. But we have seen when they do not take care of some of these things, they made devices, you get a Schottky barrier which is extremely leaky. So, now let us take one more phenomena, because these two actually, the image force lowering effect and the quantum mechanical tunneling effect join hands together to spoil the reverse characteristics. Okay. Now, if you recall, what is this quantum mechanical tunneling? This is the fourth phenomena that we are discussing now, the causes for ideality. But by now, you must have understood that the non-ideality is more dominant in the reverse direction than in the forward. Forward, there is a factor n coming up, which is slightly more than 1. It will not be 1, 2, 3 and all that. It will be just 1.05, 1.06 of that order because of these effects. Okay? But it can kill if you do not take care of those peak electric fields. If there is field crowding somewhere, okay, in the junction region, if there is any field crowding, that E peak will go up, the crowding effect. If that E peak goes up, the reverse current will get affected drastically, because barrier height there will get reduced drastically. Okay? Because after all, barrier height will get reduced more and more if the field is higher and higher. So, any field crowding effect or concentration of fields will reduce the barrier height in the reverse bias direction, and it will increase the leakage current drastically. Similarly, this quantum mechanical tunneling, this is also dominant mostly in the reverse bias. This is due to the electron which is crossing this barrier where it is thin. If you take the barrier, it is thin here as goes on away from the junction, okay, the barrier is become thicker and thicker. In this portion, if the electron has energy here, in fact, there are a lot of electrons which have energy in this portion. From here to up, there are electrons occupying. So, at this energy, there are sufficient number of electrons. So, some of them can cross here because of tunneling effect. Okay. This is quantum mechanical tunneling in the sense there is a probability that good chance that electrons can cross that. Okay. I am not getting into those quantum physics, but that is what happens. Now, the width of this barrier depends upon the width of that barrier depends upon, just 1 minute. The width of that barrier, can I sit down? So, the width of that barrier depends upon the electric field. If the electric field is large, this will vary steeply. The slope of this gives the electric field. So, between these two curves, this is at thermal equilibrium or forward bias, whereas the second curve is at reverse bias. So, when the reverse bias is there, the width of the barrier becomes smaller. The chance of tunneling is more if there is reverse bias, more reverse bias, or the chance of reverse bias is more if the peak electric field is more. If the electric field is more, this is steeper. So, whatever effect which makes the electric field more will decrease the barrier width there, and if it decreases the barrier width there, you will have reduction of the thing. So, now let us just take a look at that. Is that point clear? So, finally, what we are telling is, let us get down to practical things now. So, both the effects together will affect, they will join hands. Quantum mechanical tunneling dominate more and more when the field is high. Image force lowering becomes more and more if the electric field is high. So, both of them become more and more and the electric field is high, and definitely it is going to affect the reverse bias condition. So, let us take a look at the junction which is made like that. Particularly so, if you take an n-type material and this shaded region here, that is the depletion layer. Okay. In this portion where the metal is put directly below, in that portion there is a depletion layer which is flat. Okay. Now, when you go to the edge, there is a curvature, and the depletion layer width on the edge is smaller compared to depletion layer width here. It is much more so if there is an accumulation layer here. What I put here is some accumulation layer which can be present. Okay. There can be accumulation layer, that is n becoming n plus there, if there is if there are some positive charges on the surface. It can be contamination, or even if you have some oxide there, it can give rise to positive charges. But whether the positive charge is there or not, that is whether the accumulation layer is there or not, the depletion layer crowding effect is there. Let me just draw that once here, just to make it more emphatic. Okay. So, what I am doing is, I have this n-type semiconductor on which I just put this metal, that is a metal which forms the Schottky barrier. What we are talking of is now the depletion layer here will be practically flat. If this width were going like this, then it would have been not that much of a problem, but there will be crowding here, because field lines will all be like this in this portion, whereas from here there will be field line crowding will be there. Whether you have an accumulation layer or not, there will be crowding effect here. So, now what we are telling is that just like in the power devices we see usually that wherever junction curvature is there, you get the field crowding. Here instead of junction, you have an abrupt ending here, as a result there will be crowding effect here, field crowding. The moment you have field crowding, what happens? The moment you have field crowding, E peak is high there. When the E peak is high, both the effects come into picture. Quantum mechanical tunneling, due to that extra current, image force lowering is more due to that J naught becoming higher. So, both of them join hands together to increase the current here. So, if you make a device like this, just put a metal on silicon and make a Schottky barrier, you end up with the characteristics like this, with this thing. Because of this crowding, you end up with a characteristic which is very bad. IV will be something like that. Okay. Very highly leaky device. It will be so leaky that you won't like to see it, and or you would not like to show it to anybody. Okay. That is the state of affairs. In fact, I remember when I made my first Schottky, that was like that. Then after looking into the theory of this, what we realized is that you must cut down that field there. If you cut down that field somehow near the edge of the depletion layer, you can bring this back into this. One of the methods that is used is shown here. Okay. This is all what I have been explaining, that is WDN here, normal direction is smaller compared to this depletion layer width WDP, all that is bringing in the crowding effect. So, I said here WDN field is higher near the surface, causing enhanced quantum mechanical tunneling and image force lowering effect. In consequence, N value in the forward bias mode is function of voltage, and reverse current in the reverse bias mode JR or IR keeps on increasing. That is the curve that we have shown there. Okay. How to, this is of course a typical curve that you get. What I have plotted here on the board is shown here in typical devices that people have seen. So, you can see in this portion the current keeps on increasing, initially due to the image force lowering dominant. But when you go to larger values of the electric field, larger reverse bias, the quantum mechanical tunneling takes over, and virtually it looks like a breakdown, like in Zener diode. Zener diode, that is what is happening, it is tunneling. Okay. So, this portion is quantum mechanical tunneling, this portion is image force lowering effect. So, both together it is very bad news, in the sense you get a poor diode. Now, how to overcome that? Ideality factor n bringing closer to 1, you do not have to worry so much about ideality factor. So, what if it is just 1.01, 1.02, but what is more concerned will be reverse current. Okay. They can be overcome by two typical methods which are used in practice. Are one is actually the guarding consisting of a P plus layer put around that. Other one is the field plate. Both of them reduce the field just in that portion. Both of them try to reduce the field here, because that is the one which is increasing, which is the cause of increase in the reverse current due to barrier height lowering and due to quantum mechanical tunneling, which are due to the peak electric field increase. Okay. I will just skip this for the time being. Let us see this now. Okay, we will come back to this afterwards. That is the fifth phenomena which has some effect in the forward characteristics, not in the reverse. So, this is the P type gartering or P plus gartering. You can see the plot here shows the metal here, and this is the oxide, okay, and this is the metal put over top of that. Schottky is only here. Okay. This is actually a Schottky which is Schottky, and the junction is sorted out here through this gold. Okay. Now, how does it help? As far as this diode is concerned, I will just better draw that on the board to make it a bit clearer. See, what we do, okay, what we do is the depletion layer is here now coming, the crowding effect I want to remove. So, you put just near that, adjacent to that, a P plus gartering, and both are connected together. If you see the diagram, both are sorted together. So, when I apply voltage here, the depletion layer formed here, in the absence of this, it would have crowded down like this, there would have been crowding effect. Now, there is no crowding effect in this portion, depletion layer moves like that. Okay? The depletion layer actually spreads like that. As far as Schottky barrier is concerned, it is plain parallel, there is no crowding, all the field lines are vertical. So, as far as Schottky barrier is concerned, there is no change in the peak electric field, everywhere it is same thing, governed by the one dimensional law. So, you do not have the increase in the reverse current in that portion, in the Schottky diode portion, but you will say there is crowding effect coming up here, but now it is crowding effect in the p-n junction. The crowding effect in the p-n junction, the leakage currents in the p-n junction, okay, they are much smaller than that of Schottky diode. So, you have shifted the crowding effect from the Schottky barrier to the p-n junction, and in the p-n junction, for even if the field is higher, leakage currents are much smaller than that. So, what you have done is shifted the crowding effect from the Schottky to the p-n junction, and the current in the p-n junction, even when its peak field is higher, is much lower than that of Schottky. So, you get, when you do that, you get characteristics which are close to ideal flat. We have seen this. This is the real truth, hard truth about this is the leakage, what was like that due to leakage there has shifted up there. Other method which is popular is the theme is prevent the crowding taking place, whatever be the approach. Okay. So, this is the field plate structure. If I terminate it here, I would have had the crowding here. Now, what I do is take the metal over the oxide. See, you have got a metal here, you have got this oxide, and this is a semiconductor. Okay. Now, because it is going over the oxide, this portion where it would get crowding here, that voltage gets shared between the oxide and semiconductor. Okay. Now, let me, you see here very carefully, the depletion layer which is wide here, it becomes narrower here like that, because the voltage, I will just draw that here for clarity further. Okay. You do not do anything here, all that you do is have an oxide over which this metal will go. Okay. That is the metal. So, this is the n-type region. This type of thing people do, the tricks in the power devices, where you can, wherever there is crowding is there, take the metal over the oxide. So, now when I apply voltage here, reverse bias, depletion layer will be here like this, because the total voltage drop across the silicon. Whereas, if you go to this side, metal, oxide, semiconductor, lot of voltage drop into this, depending upon how much thick it is. So, if I had the metal going all the way up over here, it would have gone like that. But because part of the voltage goes into the oxide, this shifts down like that. So, instead of crowding and coming like this, it is spread out. So, depletion layer actually is spread out like that, so that you do not have the crowding effect. The moment you do not have the crowding effect, there is leakage current here is reduced. You have seen this also reduces the current drastically. In fact, this is simple to make. Grow an oxide, open the window, put a metal which is bigger than the window, put a metal over bigger than the window, that cuts down leakage drastically. Okay. This in practice you need to make provisions for reducing the field crowding, which would give rise to large currents, particularly in the reverse direction, due to quantum mechanical tunneling effect, image force lowering effect. Okay. So, I just one last thing I want to discuss here is the effect number 5, which is not so important, but it is being talked of sometimes. So, out of the different effects which affect the ideality, we have seen image force lowering and quantum mechanical tunneling. These are the two which really affect, particularly in the reverse bias direction. Forward bias direction also will affect, because whatever affects this barrier height, additional current, that will affect that. Now, the other one is actually insulating layer thickness of delta. If I have a thin layer of insulator, which is always present due to some native oxide, etc., that causes a slight problem. In fact, we have seen it right at the beginning. The voltage, whatever is present, gets shared between that insulating layer and the semiconductor, just like this case. If I apply voltage here, that gets shared. What we are talking of is actually a layer here, a thin layer present here. Okay. Now, let us say all those effects are overcome by the field plate, etc. You put the metal here, whatever changes in voltage you make, particularly in the forward direction, the impact is much more. Reverse direction is not going to affect, because it is going to cut down leakage current if at all anything is there. Forward direction, what happens is, when I apply a voltage here V, that gets shared between this and this. The voltage that goes to this layer is very small, because it is after all 5 angstrom, 10 angstroms. Its current can tunnel to that. Okay. So, you have got some voltage dropping across that. Now, what happens is, when I have a delta V, when I increase the voltage in the forward direction by delta V, I expect the current to increase by e to the power delta V by V t. But it will not increase by delta V, e to the power V by delta V, e to the power delta V by V t, because that delta V, if it goes completely to the depletion layer, you will have e to the power delta V by V t. But part of it goes to the, it may be 1 millivolt, out of 10 millivolts, 1 millivolt goes there. The increase in current is not e to the power of delta V by V t, but it is delta V by n V t, where n is greater than 1. So, that is the reason. So, if you have an insulating layer there, then you lose the ideality factor to some extent. In fact, in the forward direction, apart from the image force lowering and quantum mechanical tunneling to a lesser extent, that plays role in the reverse bias. So, more than these two terms, it is this layer which plays role. So, if you get 1.1, 1.15, etc., ideality factor, then you can say there is a thin layer definitely. If you get 1.01, 1.02, you do not have a thin layer. Okay. So, this particular quantity V, applied voltage is shared between insulating layer V I and the depletion layer V d. So, delta V will be delta V d plus delta V I. If the insulating layer thickness is 0, delta V I is small, you get ideal factor. So, this is another reason. In fact, I am not deriving this, you can get explicit relations between, to get the value of n from the IV characteristics. Okay. So, from the value of n, you can actually find out what is the interface state density is. I am not going through that, because it involves bit more derivations. Okay. Maybe for the time being, let me skip that thing. Okay. So, that is where the factor n comes in. Delta V is not current is not proportional to e to the power delta V by V t, but it is less than that. That is why that n comes into picture. Okay. So, finally, what we have seen, the summary of all this non-ideality factors is recombination generation current, it may have composite forward characteristics and non-saturation in IR in some cases. If you take silicon, it can affect to some extent, okay, because the J due to thermonic emission and this, the difference is less. So, it can become more dominant, or it will show up as you go to larger reverse currents, but in gallium arsenide you do not have to worry. Image force lowering, it makes ideality factor n greater than 1, not too much 1, too much more than 1.05, 1.04 in that order, and reverse saturation current will not saturate. It will become worse due to the tunneling, quantum mechanical tunneling, because that comes up if there is field crowding is present. Okay. Peak electric field goes up with reverse bias. So, that is why it is important only in the reverse bias conditions. So, both the things together are very important in the reverse bias direction. That is what I am trying to point out. Now, if you see insulating layer presence, okay, you have the insulating layer that will actually affect the forward characteristics, because some voltage goes into that. What about hole injection? You do not have to worry at all, because that is orders of magnitude smaller. Okay. But still some people have made out cases where they say maybe if you go to very, very high current densities, you may get some hole injection comparable to this one, that is the thermonic emission. Otherwise, you just do not have to worry about it. So, I think with that we have completed our discussion on the Schottky barrier diode. We have seen idealities, non-idealities, everything. Main thing that you would require is in the reverse bias operation, how does it behave, and you should know how to cut down the reverse leakage current. Those techniques also we have seen here by providing field plate, by oxide and metal running over the oxide, we can reduce that current. So, all that we have seen. Now, we will take on in the next lecture the 3-terminal device which uses the Schottky barrier as the gate, that is the MOSFET. So, we will see you next time on that.